photoelectric effect, which is evidence of the particle nature of light. Here we have a gold leaf electroscope with a piece of zinc on top. We rub a perspex strip with silk and charge the electroscope negatively. Notice how the leaf stands up. When we shine ultraviolet light on it, it discharges the electroscope, the leaf collapses. Let's see that again. Charge the electroscope negatively, shine ultraviolet light on it, and we notice how it discharges the electroscope. When will it not work? We use a piece of polythene instead of the perspex. Now the electroscope is positively charged. Notice the leaf does not collapse. The UV light does not discharge it. Back to when it's negatively charged. This time we're going to use a bright white light. But the leaf stays up, it does not discharge it. And finally, when we remove the zinc and charge it negatively as before, the ultraviolet light does not discharge it. The photoelectric effect was first observed in 1887. So what did we see today? Well, it occurs when a negatively charged electroscope with zinc on top is irradiated with ultraviolet light. Let's just look at that again. The ultraviolet light comes in and it discharges the electroscope, and we see the leaf collapses. Let's do it one more time. When did it not work? Well, it doesn't work if it's positively charged, or for bright white light, or without the zinc on top. So what's actually happening? When the UV strikes the surface of the zinc, it knocks the excess electrons out of the zinc, thus discharging it. Let's look at that animation again. The UV light comes in, the electrons are knocked out, and the leaf collapses. Why the wave theory fails to explain this? Energy is amplitude for waves, and you might think intensity of light. Here we have a particular wave. Here's the one with the same wavelength but much bigger amplitude. It has much more energy. Whereas here we have low frequency and there we have high frequency. Now the wave theory says that energy is proportional to amplitude. Here we have low frequency waves. It's probably about 15 seconds between each wave. But clearly there's lots of energy there. High amplitude. Here we have a higher frequency, probably 1 second between each wave, but it's a much smaller amplitude. Well, that didn't work for this observation. We had bright white light and fairly dim UV light. It did not work for the bright white, which you would have thought, if it was the wave theory applying, you would have thought it would have worked better than the dim UV light. So what matters is frequency. The particle model works. It was first used by Albert Einstein in 1905 using Max Planck's quantum theory to explain the photoelectric effect. It took the science world 15 years to really understand it and agree with it, and he only got the Nobel Prize in 1921. So what is this quantum theory, or the photon theory, or the particle nature of light? A photon is a package of energy called a quantum. It travels at the speed of light, we know very fast, 3 times 10 to the 8 meters per second, until it is absorbed. And then it ceases to exist. It has no rest mass. Yet, when it's moving, it can cause comet tails to point away from the sun, and therefore they do have momentum and thus mass when they move, but when they stop moving, they have no rest mass. Energy is proportional to frequency, and this is Planck's famous equation, E equals hf. Planck's constant is a very small number, but it allows us to calculate the energy of each individual photon. And a photon transfers all of its energy or none of its energy. Bright light just means that there are lots of photons, not a bigger amplitude. The photon is the smallest quantity of energy, and everything else is thus a multiple of this. And that is what we mean by the quantization of energy. The minimum energy needed to knock out an electron from a substance is called the work function, W. But this, of course, is the energy of the photon. And so this frequency is called the threshold frequency. That's the minimum frequency necessary to knock an electron out. Zinc's threshold frequency is in the ultraviolet range. A single photon transfers all its energy to a single electron, and the UV light knocks out the electrons. White light, each photon has insufficient energy. There might be many more photons coming from a bright white light, than a dim UV light, but each one is insufficient energy to knock electrons out. And this equation shows that if the energy of the photon equals hf is bigger than the work function, then any additional amount is transferred to the kinetic energy of the electron that is ejected, sometimes called the photoelectron. So where the photon has more energy than the work function, the difference goes to kinetic energy of the ejected electrons. Well, if you're struggling with quantum theory, look what happened to the two of them before and after. And the conclusion is, quantum theory is bad for your hair. Well, there are applications of this seemingly insignificant observation, and the biggest one, of course, is that of the PV, photovoltaic cells. So photons strike these panels and knock electrons out of the surface, and it passes through a circuit before returning to the cell. And that's how we make electricity from the sun. Here's a picture of the International Space Station. This thing here is the size of a building with these huge solar panels that collect sunlight. Here is the space shuttle, just having visited the space center, or the space station, shall we say. And some astronauts came, got in here, and this is on its way back to Earth. How do photocells work? Again, they knock electrons out of the surface of the metal, they pass through a circuit and return to the other side. At home, we use this electricity, which is direct current, to charge batteries and to get it ready for appliances that are used to alternating current. It passes through a thing called an inverter in order to make alternating current. Another picture. So what is light? Well, it's certainly beautiful and colorful, and its energy, it's magical. It's produced by energized matter, electrons that are jumping between energy levels in atoms, travels as an electromagnetic wave, very, very fast, 300,000 kilometers per second. It can travel through a vacuum and different media. It can be reflected, refracted, polarized, and diffracted. It imparts energy as small packages called photons. And it's these packages of energy that are particle-like. And that's it so far. Thank you for joining us.